Hi, this video covers section 9.3 from your text and really covers two concepts. The first one is how to simplify radical expressions, and then the second one is how do we add and subtract radical expressions. So the first concept, simplifying radical expressions, this is a really important concept that you're going to need to know moving forward, especially when we get into quadratics in the next chapter, and we need to be able to work with a quadratic formula. We need to be able to simplify stuff like this first example. And then one thing I just want to point out here at the beginning is to notice that we did make this assumption that all variables are non-negative. Remember, that means that we don't need to worry about the absolute value. And so this first example, there's a couple of different ways to do this. A lot of people learn it this way, though. They learn how to take the number inside here, and what they do is they factor it. And so like you could use a factoring tree if you wanted. For example, we know that 50 is 2 times 25, and then of course 25 factors into 5 times 5. And now we've gotten down here to the bottom where 2, 5, and 5 are all prime numbers. So I could rewrite this radical 50 as 2 times, and since there's two 5s, that's 5 squared. And we can't take the square root of 2, but the square root of 5 squared, remember, is just 5. So the square root of 5 squared, I can pull that out in front, and then the radical 2 stays underneath, because that is not a perfect square. Hopefully that makes sense. Let's look at another one that involves variables this time. So again, we could do the same thing with the 20. The 20 can be thought of as 4 times 5, and then of course 4 is 2 times 2. And then let's just make a little side note here. Remember that we can take the square root of something like x to the 6th. Remember, we just talked about dividing this power 6 by 3, so its square root is x to the 3rd. Or for example, the square root of x to the 8th would be x to the 4th. But what about when we have something like this example where we have an x to the 7, it's an odd power. Notice both of these right here, we had a 6 power and an 8 power. Those were even powers. If we have an odd power, what I like to talk about doing is peeling off an extra x to make it look like an even powered. So if we take this, we could rewrite it as, first of all, we could rewrite the 20 as 2 squared times 5. And then we could rewrite the x to the 7th as x to the 6th times an extra x. There's still 7 x's there. There's 6 here and then 1 here. So there's still altogether 7 x's, or x to the 7th. But now we have some pieces that we could take the square root of. Now the 6 out front, it's not specifically written, but we know that that's multiply. If there's no operation shown, then we assume it's multiply. So this is going to be still 6, and now it's going to be multiplied by the stuff that we can take the square root of. I can take the square root of the 2 squared. The square root of 2 squared is 2. I can't take the square root of 5, but I can take the square root of x to the 6th. We know that that would be x to the 3rd. And the stuff that's not highlighted there are not perfect squares. Those pieces are going to stay inside. So this is going to be a 5, and this is going to be an x inside my radical. And so I could go one step further. I could simplify the outside. We know, of course, that 6 times 2 is 12. So we have 12x cubed times the square root of 5x. We got one more simplification problem here. Again, if we do the same kind of thinking, we could think of this 24 as 6 times 4. And then we have 2 times 3 and 2 times 2. So we could rewrite what's underneath this radical. Notice there are 3 2's. So we have 2 to the third. We have 1 3. We have x to the third, or the 33rd power. We have y to the 6th power. We have z to the 50th power. And we have w to the 18th power. Now we want to talk about rewriting it in a way so that we have things that we can pull out. For example, on the 2 here, we have 3 2's. Well, I can only take the square root of an even power, so I can take 2 squared times an extra 2, and you could get in the habit of actually writing this from the very start if you wanted, rather than writing as 2 to the cubed, or 2 to the third power times 3. You could have started out as 2 squared times that extra 2 that we peeled off, times the extra 3. Now peel an extra x off, so we have x to the 32nd power times an extra x. We can leave y to the 6th, we can leave z to the 50th, and we can leave w to the 18th. But now we can pull stuff out, because the square root of 2 squared is 2. The square root of x to the 32nd is x to the 16. Remember, we just take 32 divided by 2. Square root of y to the 6th is y to the 3rd. The square root of z to the 50th is z to the 25th. Square root of w to the 18th is w to the 9th. And so we've taken the square root of all these perfect squares that are highlighted here. The stuff that's not a perfect square is the stuff that stays inside. So 2 times 3 is 6, and then we have that leftover x. This is about as difficult as the example that you're going to see, but definitely something that's doable. So now would be a good time for you to go ahead and pause the video and go ahead and try. I would do the first 3 problems of your self-check. You should be able to do A, B, and C. So go ahead and pause, and we'll see you back here in a sec. Okay, so now that we've talked about simplifying radical expressions, let's go ahead and move to step 2, adding and subtracting radical expressions. This is our second concept. And the main thing to remember is that when you're doing this, we have to think, just like from beginning algebra, we have to think that we're combining like terms, and we have to think of, instead of the like terms, we're going to think of them as like radicals. Like radicals are radicals that have the same index and the same radicand. So for example, in this first problem, since we have a root 3 and a root 3 and a root 3, those are all three terms are like terms. Now this third term, we want to think of the number in front here, even though it's not visible. We have to think of it like there's a little 1 there. And so when we go to add, we're really just saying, okay, well, what's 9 minus 4 plus 1? Well, 9 minus 4 is 5, and if we add 1 to that, we have 6 square root 3. This problem is identical in concept to the problem 9x minus 4x plus x, which we know is equal to 6x. So just kind of keep that in mind. It's the same concept. So if you look at example B, you'll see there's no like radicals here. There's no like terms that we can combine. However, what can we do? We can simplify, because we know that 18 is 2 times 9, and of course 9 is 3 times 3. And so that first term can be rewritten as a times the square root of 2 times 3 squared, because there's 2 3's there. And then here we have 7 times the square root of 2a squared. Can you see what's going to happen here? The 3 squared comes out. Square root of 3 squared is 3. We still have the a that was already out there. What's left underneath? Well, just the 2. Look at the next one. Well, a squared can come out. The square root of a squared is a, and again there's a square root 2. Now one thing I want to mention here, in order to be able to combine these, not only do we need to have the root 2's be the same, but the variable part also needs to be the same. So they both need to have also that a. And so these are like terms, and they simplify to 7 plus 3 is 10 a square root 2. And we have one more problem here. Last one is going to be, again, a similar type of concept. Think about how to factor 12. 12 is 3 times 4. 4 is 2 times 2. 27 is 3 times 9. 9 is 3 times 3. And of course, we know the square root of 9 for that last one. So if we wanted to rewrite it, we could rewrite it. The first term is 3 times 2 squared. And then this is one of those ones where we need to peel off an x because we have an odd power. So we have x squared times an extra x. Second term, minus 6x times the square root of, well, we have 3 3's here, so can we think of it as 1 3 times 2 more 3's as an x. And then lastly, we can take everything out of that last term. The square root of 9 is 3, and the square root of x squared is x. So, pulling our perfect squares out, the square root of 2 squared is 2. The square root of x squared is x, which leaves us with a 3x inside. In our next term, we have a minus 6x times, what can we pull out? Well, the square root of 3 squared is 3. What's left inside is a 3x. This is 2x square root 3x. Minus 6x times 3 is 18x square root 3x plus 3x. Again, we have two like terms. We have x root 3x and x root 3x. What about this x over here? Is that a like term? It's not. It's different than these first two. So just combining the first two, 2 minus 18 is a negative 16x square root 3x plus 3x. And that does it for this